Hello, Assalamu alaikum. This is Fahhaam Aatir from Air University. I am currently in the fifth semester of my bachelor's in Mechatronics Engineering. So, today I'm here with you for a project that is related to the subject of microcontroller and embedded systems. And basically, what this project is that we were giving this as a substitute of our mids and final exam. So what we're supposed to do over here is that we are going to build a line following robot that is going to have these five basic features. So the first one includes is that it should follow a black line using three IR sensors. So this is a very common procedure that is used for a line following robot. You have your infrared sensors that are attached to the front of your car or your robot. So what these sensors do is that they detect some sort of line or some sort of environment in which they are placed, and then they give the corresponding output towards your motor, which drives them either forward, either towards right or left. And depending upon your situation that you give it to it, or depending upon your coding, it basically can stop as well. The next objective that includes is a simple air controlled air conditioning system that is to be monitored using an LM35 temperature sensor. It is a very common used commercial sensor that is applied in our daily lives as well, in terms of industries and daily households. So this is a rather very simple tasks. The next one is the speed control of the motor with the help of an PWM. So basically what a PWM is, a PWM is pulse width modulation. So what this does is that depending upon your circuitry or depending upon your coding, you can basically control the speed of the motors. So for example, if you're going in a specific speed zone, or you're going somewhere where there's traffic or anything, so basically you can control your speed of the motors that are attached with the help of this command, which is the PWM. The next one is a simple hurdle detection system. It is that it will detect any obstacle that comes in front of it, and it is going to be displayed on the LCD. So basically, if you have an obstacle in front of you, it is going to detect it with the help of an ultrasonic sensor, most probably, or a sonar sensor, and it is going to basically detect that obstacle, and it is going to tell you the distance from it. And according to your coding, you can basically tell whatever it needs to, and it will stop at that specific distance. Like you can set it that if you have an obstacle that is 5 meters away from you, so you can set a condition that if the obstacle comes within the range of 5 meters, you can ask the robot to stop right there. Last but not the least, you have the serial communication. Basically, you're supposed to have two microcontrollers. You can use either of them. You can either use the AT Mega 328P, or you can use the AT Mega 2560. So you're supposed to do the serial communication through both of them. And basically, what you do is one of them is the master, and the other one is acts as a slave. You can either do it through the help of an SPI or a UART USART or the I2C. So the master basically takes and gives commands to its slave, and the slave basically is connected. Generally, it is connected to an LCD, and the LCD displays whatever information it has to be taken from its master controller. So now moving upon to our Proteus simulation, you can see that this is our so-called circuit. So basically over here you can see we have the ATmega 2560, which is more commonly you may know it as the Arduino Mega. It is a very commonly used microcontroller if you need multiple ports. And over here you can see it has a lot of ports, like it starts from A and it goes till L, to be honest. And so it has this many ports attached to it. However, over here you have a smaller microcontroller, that is the AT Mega 328P or the Arduino Uno. And as you can see, it has only three ports, B, C, and D. So this one has only three ports, however, this one has numerous ports. So depending upon which application you want to apply, you can use either of these. The syntax is pretty simple, and the knowing how to get to it is also quite simple as well. So moving upon our first task, which was the following of a black line using three IR sensors. So if we move upon to our simulation over here, you can see that these are our switches that will act as our IR sensors input. You have the left sensor, the right sensor, the middle sensor. All of these are connected to the resistors in order to provide some current to it, and we have a battery that gives them the general current or the voltage. You have a simple motor driver over here, the L298. This is basically a very common motor driver that is used to power two motor drivers at a time. You can see the output of these motors, out 1, out 2, out 3, out 4. They have been connected to the motors that you have over here in out 1, out 2, out 3, and out 4. So this is just the motors that are here, and you can see that they have been labeled as right or left. So the basic thing that's happened is when your right motor moves and the left one is stationary, so basically your robot is going to take a left, and if your left motor is in the running condition and the right one is stationary, then your robot is going to take a right. So in order to clear that confusion, you can see over here we have our indicators that indicate if the robot is going to take a left or a right. So it is going to show which turn or which command it is going to execute. In terms that these both motors are running, or on the LEDs over here, you can see that the both lights are running. That basically means that they're going straight, like the robot is going straight. And in case both of these lights are off or turned off, and similarly the motors are going to be turned off as well, that indicates that the robot has stopped due to some conditions that we're going to see in the upcoming video. So if I basically just run this simulation, you can see over here that this motor has started. So right now you can see that the left sensor is basically open, and corresponding to it the left motor over here is running. So as I said before, that when the left motor is running, the robot is going to take a right. So that is what is indicated over here by our LCDs, sorry, LED over here, that it is going to take a right. Similarly, if I turn on the right sensor, so now what happens is that when you have the right and the left sensor, so now your robot is going to move straight. So now you have the right motor that is working as well, and the left motor is working as well. And when both of them are doing so, it is going to move straight. You can also have see this with the illustration of the motor over here of the LED lights. You can see that it is going to be straight. Now, if I turn off the left sensor, this indicates that only the right sensor is working. So now what happens is that in a few amount of time, this right sensor is going to work, and this left sensor slowly, you can see the motor turns off. And so over here, as I said, if the right motor is operating, then it is going to take a left turn. So that is basically what is happening over here. If you move over to our motor driver, which is the core of this operation, this motor driver has been connected to the microcontroller over here, that is the 2560. So if I just zoom out a little bit, you can see that these three ports, sorry, the four ports that are supposed to be taken as input, these inputs are given over here, right over here in the port D. So you whatever the information you get from these switches over here, it is received over here in the port A, and then what happens is that it transforms it over here to PD, which is basically the output for the motors, and it gives you how the motors are going to be driven. You have the LED left and LED right. This is basically just a simple way of telling which LED is going to be turned on if you want to take a left or if you want to take a right. So moving upon to our next task, which is the climate controlled air conditioning system. So in the simulation, if I run it again, you can see over here that these are our sensors, and over here we have our first sensor. This is the LM35 that is giving a value of 51. So what happens is, so we have our LM35 temperature sensor over here that is going to give you a value on this LCD right here. So basically you can see the temperature over here is 51, and this the temperature over here is going to give you 51 as well. Similarly, if I increase the temperature, like for example if I go up till 85, so now we will see that the temperature that is going to be displayed is 82. This is for the previous one. Let it refresh for a while. So now the value that it is going to give for the temperature is 84. So it is almost close to what the actual temperature it is sensing over there. So if we come towards your temperature sensor, you can see first over here the simple VCC has been given of 5 volts right here. Then you have its sensing that has been, or the output you can say this has been connected to temp. So the temp button over here is the, you can see right here that the temp is connected over here to the ADC5. So ADC is basically a converter. It takes your values in analog and then it further uh, like it takes in the analog binary version and then it converts it into the decimal value that we want. So that is what happens here for the LCD. You can see that we have a potentiometer over here. This potentiometer is actually used for controlling the contrast of your LCD in real life or in on the hardwares. Then you simply have your pins over here from D0 to D1, D2 till D7. These are connected over here on the PC, that is the port C over here. This has been connected from D0 till D7. Similarly, your RS, the RW right one, and the E for enable, all of these has been connected over here in port G. If you want to understand what these, how these are connected, then you can come over here. This is the lcd.h. Dot H indicates the header file. You can see that these have been connected in the G and C respectively. So this is what is happening with our LCD and or LM35. Moving upon to our next task, that is the motor speed control with the help of a PWM, the pulse width modulation. So now over here, if you go towards the simulation is running, you can see. So now you can see that this is your PWM motor whose speed is to be controlled. So now over here in the uh, small screen over here, you can see that the speed of this motor as of now is 40.9, and you have the switch controls over here. So basically if I just press one of these switches, so what happens is that the speed of this motor drastically decreases. Like it keeps on going. I think it will go till about zero, almost like the motor is going to be completely shut off. So now if I turn this back on, and if I turn on the switch that is placed in the middle, so now you can see that the value of this motor is almost 23.7. So this is approximately half the value which is expected in its complete 100% mode. So basically you can have these modes allocated by yourself, that what do you want. If I turn off this again and give it the last value, then you can see that the motor is going to go up ahead at full speed, that is almost 41 revolutions per minute, and that is going to be the top speed, that is the 100% when it is connected to a PWM system. So the PWM over here you can see is actually connected to an Arduino 328 that is over here in the D port right here, the PWM. And then for the switches you have the PWM0, PWM1, PWM2. So you have the configurations over here in the PWM0, 1 and 2. So this was just a brief control from my side at 0%, at 50%, at 100%. So basically you can see that you have at least one, two, three, and four ports that are available here for using. So there are four ports that can be actually utilized in order to control the speed of the motor in a more effective way. However, if you're looking for a more advanced solution, such as those with the multinational company or those who are using the automobiles, you can actually use these ports over here in the port B and the port C as well if you wish that you want to have more control over your motor. In my case, I have just selected three states, the 0, 50, and 100%. In case you want more states, you can simply just add over here in the four empty slots that you have, and you're not going to need much of coding or much of programming. However, if you wish to add more control or you want to have a more advanced control over your motor, you can just add your PWM's motor commands over here in the ports that are empty, and you can control your motor in a way that is more customized for yourself rather than being it uh, you can say industry settled or anything like that. So moving upon to our next task, that is the robot should have a hurdle detection system. So a hurdle detection system is basically an obstacle sensing system that is either accomplished with the help of an ultrasonic sensor or a communication sonar sensor. You can also use an infrared sensor, but that has a lot of complications because it has a very limited range. So if you wish that you want to accomplish a good sensing technique, then it is recommended that you use the ultrasonic sensor or either the sonar sensor. So moving upon to our simulation, you can see over here we have the distance sensor. So the distance sensor over here, this is actually working for us as an alternative for the ultrasonic sensor in real life. So now you can see that over here we have the distance displayed. So you can see that the like first it gives you the temperature because of the temperature sensor, which I have already explained before, and after that it explains you the like it gives you the distance of uh, the obstacle that is in front of it. So now you can see that it is 25, and if I just like decrease the distance over here, or if I ask the obstacle to come near it, so now you can see that the distance that this LCD is going to give is, it gives you the obstacle ahead symbol or the indication. So now if this program is going to run again, so you can see that the temperature is indicated as 84. The distance is given to you as 2. So this is a very close distance to your obstacle, and it gives you the indication that the obstacle is ahead of you. So since your obstacle is in front of you, your motors are going to stop working. It isn't taking right, it isn't taking any left, and your motors are going to stop right there in order to avoid any contact with the obstacle. However, if I now again start to increase the distance from the obstacle, like let's just say I'll take it to about 75%. So now, like just give it a moment to refresh. So now you can see that the motors have turned on again, and depending upon your switches over here, the motors are going to operate. So while the time that your obstacle is in front of you, or that the obstacle sensor is detecting any sort of obstacle in front of it, your motors are going to stop working. Your LCD that is integrated is it is going to show you that the obstacle is very near to you, and your mobile robot is going to stop right there in order to avoid any sort of contact. Furthermore, the pins for this are pretty simple as well. You have the ground over here at one pin. On one of the pins, you have given the simple 5 volt, and on the potentiometer, that is actually the range detecting sensor, you may say, you have the distance probe over here. So if you go towards your microcontroller, the 2560, you can see over here that the distance one has been controlled with the ADC0. So ADC, again, it is the converter that gives you the value converted from analog to digital, which we can read rather than machine language. So this is just converted to another ADC port, and it is going to give you the value, and it is going to display over here according to which your robot can move across. So this is just a simple simulation that is done for our robot. Like if you are to implement it over a car, then this can be done over there as well. This is a very simple one. You have your, again, I'll go over it in a brief. Like you have your motors, the motor driver, the switches, and the left turn and right turn indicator. So this is the task first one that was going to be completed. Then over the next one, you have the temperature sensor that gives you the temperature onto your LEDs. The fourth one is the distance sensor over here. It basically detects an obstacle in front of it. It gives you the distance from its current point to the obstacle that is in front of it, and then it displays whatever distance it is on this LCD. And if, again, if the obstacle is near it, it is going to stop its motors. The number third one, we have the PWM motors. Like this is the PWM motors whose speed was controlled with the help of these switches. And as earlier I have mentioned before, if you want to add more control over to your PWMs, so you can use these unused ports, or either if you want to have a more advanced control over your motor speed, you can use these unused ports as well. So the last one, which is the serial communication, this is what I am going to be explaining in code. This is something that does not come upon in simulation, like it is very hard to detect from here. So basically what is happening is that this over here is the master, and this over here is the slave. So whatever this microcontroller is telling this slave to do, it is going to operate, and that is why you have all these values displayed on the LCD. If this serial communication is not working, then it is not possible for two microcontrollers to work in the same environment. So this is what is happening, that this master is linked with this slave, and vice versa, this slave is linked with this master. So it is because of the serial communication, or the serial, you may say, connections that is held between them. I have used the SPI, that is the semi peripheral interface, because of which it is commanding and it gives you the value on the LCD. I will explain that in my code over here. Okay, so moving upon to our code, this is, yes, the final code that I have completed from my side. So starting up all, you have the definition of your crystal frequency, that is the 16 megahertz. This is the frequency of our standard microcontrollers that are being used. So this is like for almost every microcontroller that you use, it is a 16 megahertz. But this is not fixed that it is going to be 16 megahertz, but in most cases it is. Then you have the general libraries that have been included, the input output library, and then you have the lcd.h, which is our own library that has been added and written by us. Well, it is not written by us, it has been given to us by our instructor. But this is a library file that has been created by ourselves, and it is not given by this Atmel Studio. So in the next lines, you have the define MOSI, MISO, and SS. So basically, what these pins are, the first of all, we have the master out slave in. This is the pin upon which it has been set. This is the master in slave out, and then you have the slave select. So this is just a definition of how your pin configuration is going to be for the PWM control. Then you have the function calls over here, like what functions are you going to define further ahead in your program. You have the sensor motor direction, which was our first one. You have the set speed, which is the PWM, that is third one. Then you have the read temperature, the second task, the read distance, that is the fourth task. Now, many of you might be wondering that where is the fifth task, the SPI one. It is selected right here. This is the SPI master, and we have its code right here at the very bottom. So moving ahead, we have just declared global variables to define the certain parameters. We have the distance, we have the temperature, then we have simple blank arrays, temperature and distance, so that we can display whatever value we want to them, which has been given to them by the ADC. Coming into our main loop, the int main. First of all, you can see the DDRD, which is used for the direction of the port. So basically over here, you can see the 0 cross FF, as many of you may be familiar or maybe not, but the 0 cross FF. So the FF is basically used to declare that your ports are going to be output. Basically, FF indicates 1 1 1 1 1 1 1. So 8 times it is 1, that is going to be FF. So you have three ports over here, the D, G, and C. So on the D, you have your motors, and on the G and C, you have your LCD. So that is why it has been configured like this. Then you have your DDRA, upon which you have your sensors. So for the sensors, you have the 0 0 0. 0 is basically input. So you need to get input from your sensor. So that is why we have declared 0 over here. Then this is the simple command, the CMD and LCD init over here in the, I'm going to later explain it, but these files or these commands are simply just to initialize the LCD. And this is again just a function to call your API master. Moving up ahead, you have your basic initializations. Your temperature is going to be given you by the read temperature function, distance by the read distance. You have the speed set that is going to be done by the PWM. Then you have your if statements. So what happens is that your if statement, which I mentioned earlier, that if the distance is going to be greater than 5 from your obstacle, then your motors are going to run and they're going to use the infrared sensors in order to communicate with your motors. Otherwise, if your robot is within the range of 5, like the distance is not greater than 5 and it is within 5, your motors are not going to work. So this is just a standard if condition, that if the obstacle is near you, your robot is not going to run. Then you have the simple integer to string conversions for temperature and distance in order to get you the output on your LCDs. Again, simple, the LCD data string to print the temperature upon your LCD, and the LCD distance in order to print the distance on your LCD. The CMD again is just it is just a function from your header file in order to clear the LCD. Coming towards our motor direction, you have the pin A, which had the sensors. So starting from here, you can see that this is the least significant bit of your port. So basically what happens is that or 0 indicates strip on the sensor and a 1 would indicate no strip, or it indicates a blank white space. So basically you have 0 1 0 is that when you have strips on your left and your right, however your center is blank, and then you have another one in which your strips is in the middle and you don't have anything on your left and your right. So basically you have a strip in the middle, or you have a white blank in your middle, which is the above one statement. Then your robot is going to move straight. This is just the binary conversion over here, like 0010 gives you 0 cross 2e in terms of hex, which is so hex is basically what is read by your microcontroller. So that is why we have to put hex over here, and we cannot put random decimal, or we cannot put the exact binary uh, combination that we want to put. We are supposed to get it from the hexadecimal. Then you have other conditions over here, that if it is on the strip is on the left and the strip is under the left, then your motor is turned left. Similarly, for strips on right or under right, your motor goes right. If there is no strip, then your motors are going to go forward. So basically what happens is that your robot is going to just go ahead, and it is going to keep moving forward until it finds a strip, in which case it is going to obey one of these commands. Like if it is going to find any strip or any strip combination from these, then it is going to obey these command. However, if there is no strip, your robot is going to just flatter around here and there, and it is going to find a specific strip on the environment. But then if you have a strip at all sensors, then your motors are going to turn off. This is so that your robot may not collide anywhere where it might be headed. So this is just a simple syntax in order to stop your robot from going here and there. So the next command that you have is the read temperature function, which is going to tell you the temperature, which was our task 2. So first of all, you have the add mux register. This is basically just a reference to select your voltage source to the ADC, which is your conversion. You have the mux 0 and mux 2, which are basically the multiplexers. And then you have the reference 0, which is just the enable pin. Then you have the ADC SRA. This is to enable all the features that are in the conversion ADC, and it basically enables all the input output ports, and it also helps you for the interrupt. For those of you who are having the basic knowledge of microcontrollers, you know what an interrupt is. If you don't know what an interrupt is, I have already shared my previous video about the lab experiments. Over there I had explained the interrupt. So if you're not understanding what an interrupt is, you can go up there, and I think it was the lab number 7 in that section in which I have explained the interrupts. So again, this is just the enable register, the interrupt register. This is just the basic thing that the ADC-SRA does. You can even find these registers online. These are going to be mostly given to you by your instructor, and they are there in your manual or in your data sheet, and they are there to help you provide in which mode you want your microcontroller to work. Then you have the DIDR, which is basically for enabling logical high or logical low at the specific pin. Over here you can see it is the ADC5 in our case. Uh, so whatever value you get on the ADC5, it is either going to enable it to be logical high or logical low. So this is what is done by your DIDR. So the DIDR is basically, it is so your DIDR is the digital input disable register. So whatever value you have over here, you have a 0, it is going to enable it. If you have a logical, like the logical low is the 0, it is going to enable that. If you have a 1 over here, which is in our case we have given it 1, then it is going to enable the logical high. So then you have the simple ADC SRA, that is used for the conversion start. Then you have the while loop, and this while loop is going to be executed until all of your data has been converted. So this is just a waiting procedure, and then when all of your data has been converted, your output is basically given into a theoretical formula. From there you get your output, and your output is returned. And what happens is, when your output is returned, so where your function is getting called over here, the int read temperature, and over here where the temperature is getting your value from the read temperature, you get your output over here and it is displayed upon the LCD. Similarly, for the read distance, it is again very simple. You have the add mux, which was used over here as well. Then you have the ADCSRA, which is again very similar to what you have used. In fact, the very same thing. Again, you have the DID-R0, the digital input disable register, which is used again in the very same content. However, this is used for ADC 0 pin. Over here, it was used for ADC 5 pin. Then you have the output. You have a different formula for your temperature, you have a different formula for your distance. So the value that is given to you by the ADC is now getting divided by 20, and your output is at the end getting returned. So what is happening in this if statement is that when your output, your distance is going to be less than 5, your LCD is going to display the obstacle ahead function and your motors are going to turn off. So this is something that I've already explained in the main function over here, that if your distance is greater than 5, then your motors are going to work. So this is exactly what is done here. Just a backup clause, that this if this if this very statement does not run or it malfunctions, then you have a backup if statement right here, the if statement. So this if statement is going to turn off the motors. So this is just a backup if statement that has been added in order to not run anything. Then you have the set speed for the PWM. This is very simple. These were the switches 1, 2, and 3. You can select 1 or 2 or 3, and depending upon your switch, it is going to give you the respective speed. You have 55, 155, and 255. This is supposed to be 55. So you have the 55, 155, and 255 over here, and this is going to be your speed for your motors. Then you have the send data and the master, which were your fifth and final task. So first of all, over here you have the DDRB, that is going to declare the master out slave in, the master in slave out, and the slave select. So that has been done and the direction has been given to it by this register over here. Then you have the SPCR register that is used for indicating that whether this is a master or a slave. And over here you can see that it has been selected as a master, which is the same as our code over here that says SPI master. So this code over here is done for the master one, which is loaded into the 80 mega 2560. So moving ahead, there is nothing to explain. If you want to go over the LCD header file, this is just simple. Over here, I had explained that your G and C are used for the LCDs. Over here, it has been again confirmed that your C and G are used for your LCDs. You have defined your ports, the PG0, PG1, PG2. Then you have your simple commands, like as I said, the CMD, this is used for clearing the LCD. Then you have the CMD, which is used for enabling your um, LCD. So this CMD, sorry, the init one basically clears your LCD, and the CMD one enables your LCD, like it turns on your LCD. Then you have the LCD data. You can give it whatever data you want to, and it is going to display upon the LCD. Then you have the LCD data string. So the data is for something that you want the LCD to receive. So it is going to display whatever data it gets on the LCD, and this string over here is just a random or an easy method. Like you can just put, like over here how I have done, that I have just wanted to print temperature, so it just gives me whatever temperature it has. So that is what is going to be done by your LCD, and this is just a very simple header for the LCD that had been given to us by our instructor. Moving on to our report, the report doesn't have anything special, like just the general introduction of myself, my instructor, my department, and the university. Then you have the general introduction, and like I have already explained the objectives, what we want to do. The introduction has already been given to you, what an IR sensor is, what a temperature sensor is, the PWM control, just our graphs and the duty cycles in order to explain better who want to get this report. Then you have the SPI that is used for the serial communication. You have its advantages, then you have its block diagram, how the master operates and how the slave operates. So this is something. Then you have the calculations that have been done for the distance, as it was mentioned in the code over here. Right there, this was ADC divided by 20. This was already pre-calculated by us, and it was ADC by 20. For the temperature, you had ADC 2.1 plus 1, and over here you can see it was ADC divided by 2.1 plus 1. Similarly, there's nothing over here. I have already done the theoretical explanation long ahead in this video. Then you have the block diagram. It is a very simple block diagram. Like if I can just get it to rotate from. So here we go. Here we have its rotated version. So first of all, you have the AT Mega 2560. It has three inputs from the ultrasonic sensor, from the LM35, which is your temperature sensor, and your three input IR resistors that are used as your sensors. This was the three tasks. Then you have the output over here, that is the L298, and you have your motors attached to it, the left and the right. Then you have the serial communication through the SPI that gives it to 328p, and your final output is obtained here on the LCD. So this is just a simple block diagram of the problem that we have just illustrated. Then you have the flow chart uh, of our circuit. So from here you can see that okay, so from here you can see you just started, like as I explained in the code, the crystal definition. You include the libraries, you call your functions, the variables, then you have your while loop, then you call the temperature, then you call the distance, and from distance basically again you have the condition that if your distance is greater, then it is going to call your direction, and further ahead it is going to move forward, right, or left, or stop. But if this is a no, then it again goes into the loop. After redirection, it basically displays all the things that have been listed onto the LCD, and after that it goes again into the while loop and displays everything that it wants to do again. The temperature is over here, like you set the add mux, which was the multiplier. You have the EDC, SRA. You wait for the conversion and you obtain your output. Similarly, for the distance, you have your set speed, your set add mux, your enable, and then you have the conversion, and then you have the output, and finally you have the display. In between, you have your speed set that is done by the PWM. So if your first button is pressed, you have your percentage of PWMs. Your second button, you have your second percentage of PWM, and on your third button, you have your third percentage of the PWM. Lastly, in this report, we just have a code. This is the LCD header, and this is the main code. If any of you would like this from here, then you have just the simple screenshots that I have already shared. So this was just a basic introduction for the project or the lab assignment that I have done as a part of this semester. And if you want to see more of these, so hopefully I'll be making more of these in the upcoming semesters, as my semester is about to end. But I hope you liked it, and till next time I wish you all the best of luck. Thank you.